Yeah. Okay, so let's get started. We're very, very happy to have Dr. Wonmin, who is a senior research scientist at NVIDIA. Prior to that, she was in Switzerland for her postdoc, and prior to that, she was in Germany at some TU Klaus something.
Kaiserslautern.
Okay, for her
It's fine.
PhD.
No, not many people can pronounce this. Yeah.
Yeah. Okay, and prior to that, you grew up in Korea, I assume. Is that true?
Yeah, I grew in
Yeah.
Korea. Yeah.
Okay, so it's we're not physically hosting her, but she's currently in California. And thank you for joining in your evening hours. And thanks everyone for participating here in Korea. It's 9 a.m., so pretty early for students, I'm sure. So I have been reading. We don't actually do modeling work, but Mamba and Mamba 2 and these other state space models are very much the hot topic in LLMs right now. And this hybrid architecture that this paper proposes also is very brand new and interesting to many of us. So we're very honored to have Dr. Byeon talk to us about her research at NVIDIA on this topic. So please go ahead.
All right. Thank you so much for the introduction. So today I'm going to talk about an alternative architecture for efficient large language models. And yeah, I'm Wonmin Byeon. I am a senior research scientist at NVIDIA. And the main part of this talk will be about the paper that we recently released on an empirical study of Mamba-based large language models. And this effort is with the many people at NVIDIA and also the authors of Mamba. So here are the contents for today's talk. First, I will briefly mention transformers and their drawbacks, and then I will talk about state space models, especially Mamba and Mamba 2, and their limitations. And then it comes to the hybrid architectures, including existing work and ours and the experiment. So as we all know that transformers have great performance. This is one of the most famous the chatbot leaderboard today, and all these top 7 models are transformers. And as you may know that a lot of companies, all these companies, including NVIDIA, try to scale transformer models to make it even better. And this is the first transformer paper, and it's titled as "Attention is all you need." And today's talk is about whether we actually need attention, and attention is all we need. In previous work, they found that transformer models performance improves smoothly as we increase the model size, dataset size, and amount of compute. And that's how now we see that it can scale really well. But there are some drawbacks. The first is the inference speed. Because it scales quadratically with the sequence length, the inference is slow, especially the sequence length gets longer. And it's because of this the basic attention mechanism that we see here, that all this computation needs to be done for all sequence length at each token, and this is a large amount of computation. To address that issue, people started using KV caching. And KV caching is basically the K and V come from the previous context, so we can reuse that. So by reusing this, we can reduce the amount of computation and improve the speed. But it also increases the GPU memory if the sequence length gets longer. Lastly, we also found that for some tasks, the model is good up to the trained sequence length, and more than that, it cannot perform well. So this is one example. So we trained this model for 8 billion parameters trained for 4K sequence length. And this is the phone number lookup task. I will talk more about this task later, but basically what it does is it retrieves the correct phone number given a name. And as you can see that accuracy is 100% up to almost 4K, and then it drops to 0 right after. So with all these drawbacks, now what can be the alternative architecture? Another option that we often use before transformers is RNNs. So the nice thing about RNNs is the inference speed is really good. So it scales linearly with the sequence length, so fast. But training is really slow because of this sequential nature. It cannot be parallelizable, which means that it cannot scale for the large language models. So people started looking into state space models lately. And this is the basic structure of state space models. It looks quite similar to RNNs. So it has input and states, and has the state matrix, input matrix, and the output matrix. And it's originally designed for the continuous domain, but it can be discretized. And here is the discretized version, and it looks just like a linear RNN. And also it can be parallelizable. I will talk more about this part later. And there is another difference. So compared to transformers, the state space models, SSMs or RNNs, has a fixed state. So it's a fixed size of state vector, and that contains the entire history, which is compressed in this small vector. On the other hand, the transformers, they have cache of entire history. There's no compression. So we see that the SSMs or the RNNs have is more efficient, but the transformer has a better performance. So now the question is, can you actually improve the performance of these traditional SSMs? And the answer is yes. Recently, the Mamba has been proposed. I think you may all know about. It has 3 main features. The one is a selective SSM, second is a parallel scan, and the third is the hardware-aware implementation. And from these features, key features, Mamba model was able to scale better, and also it performs as well or better than the recent transformers. So here, this is a scaling laws. The purple one is Mamba, and the orange is the latest transformer. And as you can see, that is nearly similar or slightly better. And now I will talk a little bit more about these 3 key features of Mamba. The first part is the selective SSM. Basically, what it does is, so here on the right side, this is the discretized states and discretized version. And what selective SSM does is that the B and C matrices and also the state size delta to discretize this ABC are dependent on the input. So this is the original one, and it becomes with the AK, BK, and CK. So all these ABC matrices depend on the time step K. And now with this, the nice thing is that now it's not like the traditional SSMs that it has just one state vector to compress the whole entire history. It has more rooms to select what histories to compress. And unlike the transformers, it's not just the uncompressed whole history. So it's more powerful compared to the traditional SSMs, but also it's more efficient compared to transformers. And then the second key features I mentioned was the pattern scan. So this pattern scan, the Mamba is not the first one introduced pattern scan for SSMs, but they show it with they combine with the other parts and show that it can be used very efficiently and it can be very helpful for scaling. So to briefly show you what it is, this is the linear recurrence in SSMs in Mamba. And if you compute this sequentially, it looks like this. But using the pattern scan algorithm, you can compute like the right side. So we can calculate the sequence in parts first, and then iteratively combine them in this tree structure. So if the sequence length gets longer, then all these parts can be computed in pattern and then combine them. And then the last part is the hardware-aware implementation. So it minimizes the copying between SRAM and DRAM. So all the states are kept in the SRAM, and all the rest of the parameters are kept in DRAM. And with these tricky features, now Mamba is more powerful because of the selective state compression, and also is much faster compared to pattern scan because of pattern scan and the hardware-aware implementation. So the good thing is that now the inference speed is as fast as RNNs because it also scales linearly with the sequence length, but also because it can be parallelized, the training is fast as well. The same authors of Mamba, they later introduced Mamba, the second version, Mamba 2. I won't go to the details about this Mamba 2 model, but the major part are these two things. So first is that they divide the sequence into the chunks and then do block decomposition for the ABC matrices. So the computation for those matrices are a lot more efficient. And then the second part is the architecture. So they remove all these projections for A, B, and C, and that also improve the efficiency as well. So here is all the background about Mamba 2 and the transformers. And now it comes to our paper, an empirical study of Mamba-based language models. Basically, this paper is about the study among these three models, and we want to know that these Mamba-based models can do well compared to transformers for under exactly the same setup. So we kept the model size to roughly 8 billion, and we trained the models on the sequence length 4K. And the data set we used was from this paper. It's a very recent paper. If you want to know more about the data set, you can go to the paper and check it out. But basically, roughly it contains like 70% English, 15% non-English, and 15% code. And we trained these AP parameter models on 1.1 trillion tokens. And then here is the very first comparison. It's a standard short context test. A lot of people use these tasks. And as you can see that Mamba is doing pretty well on these tasks, except this one is MMLU. And let me talk more about this, what it is and why it is. So MMLU is basically the multiple choice questions from different subject in zero shot and the few shot settings. And basically it gives the questions like this, and then it has a choices with the alphabet A, B, C, D with the answers, and then it provides the targets, so the model can select the one of these from the targets. And you can see that compared to transformers, all Mamba models are doing really bad in this task. And especially this, we see that this is almost random answers. So it just cannot do this task at all. So what the next trial we did was we changed the format slightly to see how well it can do. So what we did was instead of giving just one A, B, C, D in the target, we also put the answers so that Mamba, it might help for Mamba to figure out what should be the answer. But we didn't find any performance improvement or difference with this format. And then lastly, what we tried was just remove all these multiple choice questions. We just put those listed the answers in the targets. So it just selected directly from the answers in target. And from this, we found that first, transformer is not very good at this format. And second, Mamba-based model is doing much better in this setting. So in conclusion, we can see that Mamba knows the answer. The information is in there, but it's just it's not able to retrieve the information based on the format is provided. So basically, it doesn't understand the question answer format well. And for this task, another thing we tried was that initially, we trained the model on 1.1 trillion tokens, and what if we keep training? So we just trained a new model with the 3.5 trillion tokens. Then we found that it improved for both transformers and the Mamba models. So basically, in general for this task, it needs a lot more training tokens. And plus, as you could see from previous slide, that Mamba, it has a hard time understanding the format well, especially when it's trained for shorter number of tokens. And another limitations we found from Mamba is that it's a phone book lookup task. So the task looks like this. This is an example. So we provide the phone books, basically the names and the phone numbers, listed those, and then give some examples, the question with the name, and then answer is this phone number. And then we ask the model question, okay, what's the number of this person? And the model should be able to answer the phone number. And this task, we found that Mamba is doing really bad. So the orange is the transformer, and the other two are the Mamba and Mamba 2. And transformer is good up to the point that is a trained for, but Mamba is like the accuracy for Mamba drops like 10% at about like 2.5 thousand tokens. So it is pretty bad.
So can I ask a quick question? So
Yeah,
when
sure.
it says the wrong answer, what does the wrong answer look like? Is it like one of the other phone numbers, or is it just not following the instruction? Like, does it say random things?
No, it does say the phone numbers, but it's just wrong ones.
Oh, okay.
Yeah. So from those studies, we see that it's bad with MMLU and the phone book tasks. And these two tasks require in-context learning, information routing between tokens, and the copying from the context. So now we know, okay, Mamba is bad in those, but Transformer is good. But Mamba is good in other tasks, and also it has a fast inference. So can we do something about it? And that's how we started looking into the SSM transformer hybrid models. And there are some existing hybrid architectures, and for instance, Griffin or Jamba. And in all those papers, what they show is that in general, hybrid models can do better in longer sequence, and also it's more efficient in terms of speed and also memory. So they are able to train even up to 1 million context length, which all other models could not do before. So here is our hybrid model design. The first, we consider 3 different layers. First, of course, Mamba layer, and then attention layer, and MLP layers. And what we did to find the right number of attention and MLP layers, what we did was we started from the from Mamba, the pure Mamba model, and then we started adding attention layers one by one. And then we got this nice curve here on the right. So this the x-axis is the amount, the percentage of attention layers. So the most left is Mamba, and the most right is Transformer. And right at the y-axis is the validation loss. And this is this study is done on 130M model. And we found that somewhere between 8 to 16% here provides the best validation loss. So since attention layer is expensive, we wanted to minimize the amount of attentions. So we picked the minimum amount, which is 8%. And then the next is MLP layers. So MLP is in general good, like more efficient on GPUs. So we wanted to use as many MLP layers as possible instead of like replacement of Mamba layers. And then so we did a study to find out what's the good ratio, and we found that somewhere between 30 to 50% are provide a similar performance. So we keep the maximum, which is a 50%. Then the next part is the position embedding. We consider rotary position embeddings. And then we found that actually using the rotary position embedding is not very good, especially for longer sequence. So the one is highlighted is without position embeddings, and the last two are with the position embeddings. And you can see that it's better not to use it, so we didn't consider that. And these are some other details. First, about the position of attention and MLP layers. We found that there's no difference with the like specific positions of attention or MLP layers or the ordering of these layers. So we found that it's best actually just evenly spread those layers. So here is our layer pattern. M is Mamba, and the plus is MLP, and the star is the attention. But we made sure that the first layer is Mamba, so we don't need any position embedding at the beginning. So this is also studied before in other papers, and they found that also so we can just remove the position embedding if the Mamba layer is at the beginning. And then we use a GQA for efficiency, and use a global attention for better performance. Okay, so this is our performance comparison with the hybrid model on standard short context task. And you can see that MMLU is much better now, even better than transformer. And if you look at this figure on the bottom, x-axis is the train tokens, and the y-axis is the MMLU score. And somewhere up to like 1.4 trillion tokens, its transformer was still better, this orange one. And then then after the hybrid model started outperforming transformer. So eventually hybrid model is better than transformer, and also of course Mamba. Next, what we did was we wanted to study for long context tasks. So we extended this 4K sequence model to 16 and 32K sequence length. And we evaluated these models on 22 different long context tasks. Overall, the numbers look good, except this one. This is a multi-document Q&A task. And here, transformer is mostly better than both hybrid and Mamba. We think that the reason here is because in this task, they combine different documents from different places. So these documents are not necessarily connected to each other. And because of that, Mamba gets confused. The Mamba-based models get confused with this, and it's hard to find the right answers from it. That's what we think could happen. But yeah, but this is still not very good, and we are looking into the solutions, how we can improve this. And the last is the phone book tasks. The green one is the original pure Mamba model, and the orange is the transformer, and blue is the hybrid. And you can see that overall for 4K, 16K, and 32K, hybrid model is better than transformers. And the nice thing about hybrid model is that it can do almost twice longer context compared to transformers and the trained sequence length. And also we are able to extend extend the model to 128K sequence length. And you can see that the model does really good job up to almost like 180,000 tokens, which is a lot. Lastly, here is the inference speed comparison. So here the x-axis is the input length, and the y-axis is the speed up compared to transformers. And as you can see that when the input sequence is shorter, there's not much speed up here, but once it gets longer and longer, there is a huge speed up to like 7-8 times at about 140,000 tokens. So it is we see that actually it improves inference speed a lot as well. Okay, here is the summary. So in our paper, we directly compare 8 billion Mamba, Mamba 2, Mamba 2 hybrid, and the transformer models. And we show that pure SSM models are good in accuracy on most downstream tasks, except the retriever and the in-context learning. And our hybrid model and the extensions to 16 and 32K sequence length outperforms the transformers on most benchmarks, including the retriever and the in-context learning tasks. And then also we show that this SSM-based model has inference time speed up to 8 times without any accuracy degradation compared to transformer. So yeah, this is end of my presentation. Here is my email if you want to reach me out and discuss anything anything about this work. And here is our paper. Feel free to go look more into details. Thank you so much.
Thank you. I think it's amazing that you have done this work. I'm sure many people have questions. So let me ask, so people, participants who are here, if you have a question, you can either raise your hand and unmute yourself and ask, or you can write in the chat. Anyone have questions?
Hi, I have a question.
Go ahead.
Sure, go ahead.
Yeah, thanks. First of all, thanks for the great presentation. And I have a question about the long context accuracy comparison with transformer and the Mamba hybrid model. So I can see that in the transformer model, like there are some 16K and 32K, which is very different context handling. So I just wondering, what kind of model did you use and how did you make handling some context lengths, various context lengths? There are some 16K or like 4K and 32K, or did you use like a sparse positional embedding technique, or did you train yourself? Yeah.
So all these models we trained ourselves. So the setup is exactly the same. And from 4K to extend to 16K and 32K, what we did was we just continued train for both hybrid and the transformer models. We didn't change anything to the data set. But for the transformer models, we changed the frequency base of drop. So it can be adapted, the positional embedding can be adapted for the longer sequence. And we didn't do any other tricks that people do for long context. So this is just a pure, clean comparison among these models. Does that answer your question?
Yeah, thank you. And I have one more simple question, and I don't know much about the Mambas, but I'm just wondering, as you said, the Mamba-based model do not necessarily need some positional embedding like law. So could you explain more about why does Mamba do not need some ROP? Do they have some increasing ability of like separate some positional information?
It does have a naturally, implicitly, because it goes in orders, it naturally has some ordered information internally. But rope can be used in between the layers, and also it's used at the beginning of layers, right? These two are a bit different things. So for the beginning of layers, because of that reason, we explicitly use Mamba layer so that position is naturally embedded in the model. And then in the middle, we found that it was not necessary. I think it's because of the same reason.
Okay, makes sense. Thank you.
No problem.
Okay. Yeah, there is a question in the chat. How did you determine the position of the transformer layer in the hybrid model?
You mean this position of the attention and the MLP layers? So
I think so. Yeah.
As you can see that these are there's no pattern or anything. We just evenly spread out. So basically, what we did was from the Mamba layer, we have like certain number of layers. Here in this case is 56. Then we determine how many layers we need, and for the 56 layers, 8% was 4 layers. So we evenly spread this 4 attentions first, and then after that we just place the MLP, again evenly spread out. So there's no certain way of embedding it. We just it's just automatically just spreading out based on the number of attentions and MLP we need. So we also studied like specific positions, like adding attention and MLPs at the beginning or at the end or in the middle, or which ones should come first. Maybe in transformers, attention is always used like MLP layers always use the after attention, so we place that or inverse that. We tried all these different combinations and we didn't find any difference. So we thought that this is actually more natural and the easier way to just add these layers.
Jung-se Park, Professor Park.
Yeah, I'm here. Can you hear me?
Yeah.
So yeah, nice talk. Thanks for the great talk. So I have two questions, one technical, one non-technical. So first, the technical question is, it seems like it seems like you're well aware of the cases where SSM, so in terms of task, when the SSM works better than the transformer. So, but your hybrid model, but doesn't, it seems like you have actual the merge in terms of layers, like you have Mamba SSM layers and transformer layers. But one alternative for that could be when you actually do the service for the inference or something, or I mean, even if that is for on device, that you are running certain tasks that you just choose to use SSM based model over transformer, and vice versa. So why is it better idea to merge the and potentially it can be a bigger model than just the transformer or SSM model to have a better accuracy? Does my question make sense?
So you're saying that why hybrid gives a better accuracy in all tasks, not only certain tasks? Is that the right?
So my question is more of,
interpretation?
so for task A, maybe you already know that SSM based model works better, and task B transformer works better. Then you just can choose at runtime that, oh, I have a task that I just run this model. I have a model task B, then I can just run this model. Why do we need to have? Why do we need to unify the model into a single model so that we can use it for every case?
Okay. Yeah. Right. Got it. The reason is because we cannot choose every time we have a new task, right? If there is a new task, we don't know what we should use. We have a rough ideas for existing benchmarks, but it's always unknown, right? And that's one reason. And another reason is we don't want to switch. There are cases that you need both multi-choice questions and then also some generation task that you need to do in one model. That always happens in productions, and you don't want to switch the models because of that. So it's actually better to have single model can do all different tasks. That's one reason. And another reason is that we found that actually hybrid model is better for all the tasks. It's not only it's better for the better for MMLU and the copying task that we show earlier that Mamba is not good at, but also overall it actually performs better, and also it's better for the longer context as well. So those are the reasons that we are exploring these hybrid models. And also other works, not only our work, but the other hybrid models also show that this is correct. This is true.
Makes sense. Makes sense. Thank you. And non-technical question is, I'm sure that there are lots of students here working for NLP AI. And also I invited my students here, and I'm sure that there are people working on computer architecture and systems. And unfortunately, there's not much collaboration going on in school right now, but hopefully there will be later. But in NVIDIA, I noticed from your slides that there are design choices in the neural network architecture based on the hardware constraint and needs. So how do you collaborate, or how do you work with those people in NVIDIA?
So it depends. So this is the project from that we work with the Megatron people. The Megatron is the open source from NVIDIA for large scale LLMs and also other tasks like multimodal language modeling and so on. So here we have a more and less strict constraint for the hardwares to use. That we have all the baselines, transformer baselines from Megatron, and we wanted to have like one-to-one comparisons for our case, for hybrid and the Mamba case. So we didn't really think about what will be the best, like what hardware we should use, and we didn't really consider that much for this this project. But it depends a lot on like the needs actually. So but yeah, but these works are not strictly. So here we use H100 for all the experiment, but it's not strictly on that also. Does that answer your question?
Yeah, yeah. Perfect. Thank you very much. Thank you.
We should definitely collaborate. So Professor
Of
Park
course,
is
we should. We should.
right
Yeah.
right next to my office. Okay, let's get to one more chat question, and then we have 3 others who raised their hands. So this is from Kyuan Kim in the chat. Where's the length generalization capability of the hybrid model from? Where is it from? While the previous models didn't have, especially when we see the results of the phone book task, right?
Right. So it's I think it's partially because of the strength of both transformer and the Mamba models. So Mamba model, it couldn't do well in this case, even for 4K, because it cannot do well on copying task. But in general, we know that these kind of recurrent models are good for long generation. That is known. And then transformer, it is good. It is good at copying tasks, but in both copying and generations, it cannot generalize to the longer sequence. That's also pretty known factor now. So we think that because of that, this combination kind of helps each other, that it can extend the context much longer, because a lot of Mamba layers actually help for that, but also for specific copying tasks that that Mamba cannot do, the transformer is there for it. So basically, all the states of the Mamba understands understand the longer history, and the transformer is there for certain computation that is required for copy and retrieval. So that's why I think this is extending much better than both models. We didn't do any specific generation. We have a generation tasks here, but in general, this all these 22 different tasks contain generations, question answers, some copyings, and a lot of different tasks contained here. And we can see that in general, the hybrid model can do well on most of these different type of tasks.
Yeah, this is really interesting. The graphs you were just showing, plus these 2 tables. I'm sure there will be a lot of people following up on this work. Are your trained models open?
Yeah, all of them are public. Code is public, or the checkpoints are public, so you can play with it.
Yeah, that's great. Thank you. So Tae-sik Yoon?
Yeah. Thank you for great talks. I have 2 questions, and one question is related with the hybrid model. As I understood, the hybrid model can improve the efficiency compared to transformer by mixing the SSM. However, it also requires to retain the context to processing the query, right? Because it's using transformer in the middle of the SSM.
Mm-hmm.
So I think it can be one of the limitations of the hybrid model. So has this been discussed in your groups or your papers?
So you're saying that so Mamba has a linear complexity at inference, but because of the the transformers, it is that having transformer is a limitation for hybrid. Is that the right interpretation?
What I want to say, what I want to discuss is not related with the inference complexities. What I want to say is the to processing the query, the hybrid model should sustain the context. For example, it can be not problem for chatbot because chatbots already have the context. However, some tasks should sequentially input the information. In this case, SSM can drop the inputs after encoding. However, hybrid model or transformer should sustain or retain the context before processing the query. You understand what I'm saying?
Right.
So,
So
I
because
think
it is using the output of Mamba, it can be the limitation because it doesn't have the explicit the access to tokens. That's what you're saying, right?
exactly. So I think this can be some the limitations of the hybrid model. So is this also discussed in your course or some?
It was not discussed in the paper, but that is true because it still retains any limitations that Mamba or SSM models have, like for instance, if you want to have like very long sequence processing and it still have like some forgetting can happen, right? And once it's forgotten, then there is no way to recover by using attention. That is correct. So yeah, that's definitely true. It depends a lot on the quality of Mamba, basically. And so up to this point of scaling, we didn't find a lot of issue with it, but it's true. I mean, I think there is high chance also that this is, for instance, this is a potential limitation currently that with the multi-document Q&A tasks that it also cannot process well with both Mamba and hybrid models, right? So I think this definitely needs more improvement, either in Mamba or in the way it's hybrid. I think so you're totally right.
Thank you. Another quick question is about the phone book task. I am interested in the timing of the performance deterioration because performance is very dramatically decreased. So I'm curious why the performance deterioration is very dramatically happened. My expectation is this is related to the number of the length, the context length. For example, transformer using something 4K context and Mamba hybrid can use the larger context by using the mixture of the Mamba. So maybe I think there's a reason. Am I right? Or
you're right about this. So basically, if you see the pure Mamba model, it doesn't have the same issue, right? It's not good, but still it degrades smoothly compared to transformer, and it's because of the transformer. It has a limited context, which is that's totally true. And although that's why actually we use the global attention instead of local attention that a lot of other hybrid models use. So we try to keep the context length as long as possible for attention, but still I think that affects here that it just directly from 100% it goes to 0 very quickly. So you're right, but I think this can be improved by using more recent attention models that sometimes they use some memory, adding memory, or they have like these ring attentions, or like there are different ways to improve this which we didn't do anything like that here. So
you just using the live transformers for the hybrid model.
We just use a very clean, simple attention
correct.
It's not even the transformer, it's just attention layer, the single attention layer with the GQA. So with that, we believe that this can be improved.
I understand. Thank you for your answer. I'm done. Thank you.
Okay, thank you. And it's remarkable. I didn't realize that it is actually not the transformer, but just global attention. Okay, Konu, Ko?
Yeah, can you hear me?
Yes.
Thank you for your great presentation. And I have two questions. Firstly, could you describe the reason why the hybrid model's performance has improved dramatically despite the low proportion of attention operations?
I think it's because the Mamba model can mostly do well. It just needs some more capabilities to boost it up. And the attention, we know that it's especially good for certain tasks, and then it can, it has this direct access to the tokens, which is that is a very good capability that Mamba models don't have. So I think that's why even like adding very few attentions already help. Like basically it corrects the states of Mamba over time, so that over the layers it just corrects the any fuzzy memory that had in Mamba. That's I think sort of my explanation that why this improves a lot. And yeah, we are also surprised that we just need 8% of attention. That's it. And that's why it doesn't have much downside that original transformer models have.
Okay, thank you. And second of that is, does the performance get affected depending on the position of the transformer layer? And what I mean is that how you can determine the location of the transformer layer? Is it just empirical results or something others?
Yeah, that I mentioned here that we studied all different type of type of hybrid layers, that how we can actually place those layers. We found that there's no difference. So that's why these are like more or less evenly spread at random positions that we found that is the easiest for studying. And yeah, this those specific positions. So most of the hybrid models previously, they fixed the how they combine these 2 or 3 different layers. So often what they do is that they put Mamba and then they put transformer, which is attention with the MLP, and they fix that, and then they stack these 3 blocks into different to increase the number of layers. But we found that that's actually not necessary, and especially in our case, those small number of attention is enough. So we just put them roughly in the middle to make sure that it gets enough signals, and that's the only thing what we did.
Oh, the main point is that whether or not we use transformer or not, right?
You mean without transformer, just meaning just Mamba and the MLP?
No, I mean that do you mean that the main point is that the existence of transformer is important, right?
And the ratio.
Yes, ratio. Okay, thank you very much.
Yeah. Yeah.
Okay, there is a chat question, but let's get to Binu first, and then we'll get to the.
And then I'll also.
Okay. Binu?
Okay. Thank you for your great presentation. And I have 2 questions. The first question might be related to the basic knowledge of Mamba. And in the slide 15, we can we can see that BC and delta gets longer as L increases. And then can we understand these matrices as key and value matrices in transformer? And if this is yes, does Mamba show the same problem as the transformer, something like handling those caches?
So this increases the cache compared to the original SSM. That is true. you can consider that as a KV cache, but still the amount of computation is much smaller, and also size of the matrix is a lot smaller. So it's not, directly same as the KV cache in transformer. And in fact, in Mamba 2, they show the relation between SSM and the transformers, and based on that, actually they modified it to make it more efficient. So in this Mamba 2, they show that by actually doing more compression of the state, we can make it more efficient with the SSMs, but even the performance improves as well. So this is basically, you can consider it as a KB compression in other words.
Thank you. And for the second question in the slide 27, what is the main reason that Mamba can't do this kinds of, I understand this is a kind of selective copy that Mamba paper is trying to contribute. And I understand that Mamba allows selective copy, which other linear models can't serve. Then is it okay to understand that although Mamba is trying to overcome this task, it is still not doing well compared to the transformer?
That's also our answer as well. So what we think is that from this, the last setup, we found that, okay, Mamba can do it. So it's not like, Mamba doesn't know about it, doesn't know about this answer. It's just it cannot give the correct answer based on the format. That's our conclusion from this study. So that's the reason that we think that by using transformer in hybrid model, it improves MMLU a lot.
The selective copy task, you mean?
The selective copy task, you mean the in the last case?
Yeah,
or the other...
like in other cases, it all seems like the problem of selective copy that Mamba is trying to overcome. And I heard that Mamba, the most contribution is allowing those kinds of selective copy, and yes.
It does help definitely by having, so selective copy, you mean, I think is that in Mamba we have this selective states, so that
Yes.
helps with selecting the tokens, like select the tokens to compress basically. So
yes.
Yeah, I think that helps as well. I don't have direct comparisons without these selective mechanisms and with selective mechanisms, but I do think this helps as well. Yes.
Thank you.
Okay. 문재균 교수님.
Yeah.
학장님.
Thank you for your talk. I hope to have you here in person sometime soon. Get to visit.
Yeah, I hope so too.
I got a question about the fundamental scaling law. So let's say time complexity of these models, including SSM and transformers, goes like C times n raised to the power alpha. C is a constant. N is the context length, and alpha is the power, which we know is 2 unfortunately for transformer. So that's problematic, right? That's a huge problem. It doesn't scale, basically. So, but let me, if I understand.
You mean it doesn't scale because
people say scaling is not possible because alpha is 2, quadratic time complexity, something that we're not going to be able to, we're not going to, be able to have a hardware that can grow with the square root of n, right?
Right. Okay.
That's something that we have to address. Well, hold on a second. So my question is, so you have an 8x speed up, which is great. So that's like C is now, instead of 1, it's 1/8, right? Now, has the alpha changed with this? Probably not, because you're linearly mixing attention layer with transformers, right? So you reduce percentage of transformers. So it's I mean, overall speed up is great relative to transformer, but down the road, as N grows, as people become more greed, they want to, find better answers for bigger problems, and N will grow. Now, is this linear mix fundamentally a solution? Are you guys thinking of something else, that can touch alpha? You ultimately like to change alpha from 2 to 1 to, or somewhere close to 0, I guess. So that's my question. Fundamental scaling law.
Right. So I totally agree with you that this is not, not the best solution, I would say, because the adding attention is the bottleneck, and that's why this speed up kind of goes down once the context lengths get longer and longer. Ideally, it shouldn't be, and the solution is how can we combine this attention like computation, like operation inside of Mamba? That's the question, without increasing the complexity, right? And we are thinking about it. We are looking into that. But I think this is a long way research to go. So what some people actually have tried to to combine these two models a bit more smartly, that it's a hybrid the Mamba models, SSM models are good with generating long sequences. So it first to generate that, and then using transformers, it just chunks out and only do some smart way of doing attentions, so the computation doesn't increase much, but still it does same quadratic computation. So I think fundamentally what we need to figure out is that how can we remove attention? Like, how can you remove attention operation while having attention like in operation? So that will be the question, in research, in the community, like how can you improve this? That's actually the open question now. Yeah.
Yeah, I think that's
Thank
a $1
you.
million question.
Yeah, I agree.
We should all work together for the better of mankind.
Yeah. But I think our study kind of tried to show that, this can be improved. There are rooms to improve, that it doesn't have to be quadratic. That's actually that's the sort of the, starting point we are showing here.
Right.
Right.
Thank you.
Yeah, that's a good takeaway message. And maybe John is trying to also collaborate with you. So John, go ahead.
Yeah, sorry. Thank you for the talk. I wasn't gonna ask a question until Professor Moon decided to ask it, so I'll try to follow up with this question. Can you sort of provide any sort of rough approximate numbers in terms of scalability, training time, inference time, just so for us that don't have a good idea, good feel for these models? And I guess related to that, everyone knows NVIDIA has state-of-the-art hardwares, and NVIDIA has different ways of scaling their systems. I haven't seen the white paper that you guys wrote, but have you guys done sort of scalability analysis in terms of how well Mamba scales on NVIDIA GPUs?
So for this work, we haven't done it yet. This is in our to-do list that we need to do this study, but yeah, so far we haven't done it yet. But in general, at NVIDIA, people are working on it to figure out how what's the scaling law for all these models and at scale. And for us, so what we did to train the 4K 8 billion models and the 16K 32K. Initially we just did tensor parallel to train the 8 billion models. So that was our first step to train this type of models. And then for the extension, we had to do more heavy parallelization. So we did a lot of parallelization in the code to make this work. So that's why it's and parallelization is different for the different models. Like, the transformer needed more parallelization, especially even extended to 32K, we need more parallelizations, and we are not able to do it for 128K. So we cannot really directly compare the speed for training and the inference, to be honest. But that's why we only have the inference speed shown in the paper so far. But it is what we can tell is that Mamba and the hybrid models that requires way less parallelization than transformers, which means that less number of GPUs and less time.
Well, is that a good thing for NVIDIA if you need to sell less GPUs? It seems like it would be a good thing to have more GPUs. But I guess just along those lines, if you could, I guess again, this is coming from someone who doesn't have a good feel for these models, but if you could accelerate these on, let's say, the next generation NVIDIA GPUs by 10x, or from the additional memory, additional bandwidth, and so forth, what could researchers like you take away or do with additional compute capacity? Does that, sorry, it's a very open-ended question, but I just wanted to get someone's opinion on this.
Right. So for this particular Mamba-based models, the major bottleneck is let me actually go to that. The major bottleneck is this pattern scan still. So this recurrent computation that by using pattern scan made it more efficient, and then also in Mamba 2 that they try to minimize this pattern scan basically so that it can be more efficient. But this is still not the most efficient implementation that I would say, that we use directly from what Mamba authors provided, and this is not the best optimal one. And people at NVIDIA are working on improving that as well in more different GPUs, especially because this requires like a heavy CUDA implementation to optimize, and yeah, people are working on it to improve this. And this is I would say this is one of the major bottleneck that people are working on.
Okay,
I don't know
thank you
that
very
answered
much.
your question.
Yes, thank you.
You're welcome.
Okay, so there are two more questions in the chat. I think the first one, which talks about hybrid model scaling, I think we've talked enough about. And another question is, it's somewhat very different. So thank you for today's insightful introduction to the Mamba model. I primarily operate a family office that invests in AI and robotics, for example, Figure AI. Do you think there will be opportunities in the future for AI startups to easily utilize this technology?
I think so. Especially these Mamba based models or hybrid models. Let me actually go to the one slide here. Sorry about this. Yeah. So in this Jamba paper, they actually show that they can fit 140K context length in one single GPU. So this made it possible for anyone to use this model for this long sequence length, which was not possible so far. So I think there are a lot more rooms now for the startups to to try these models or do something with these models if the amount of GPU is the main constraint for startups. So I think this is this opens to everyone to use such big model for like general tasks, I believe.
Yeah, definitely. And the space is moving so quickly. Are there other questions? I don't see any raised hands or chat messages. Okay, then let's thank our speaker, Dr. Byeon, for this great talk and this wonderful, incredible opportunity to hear about your research at NVIDIA. Thank you so much again.
Thank you so much for having me.
학장님 혹시 더